In this video, I'm going to show you how to solve polynomial inequalities using a sign table, and in particular, we're going to consider the case where the right-hand side is 0. So here we want to solve this inequality, three factors multiplied together, x minus 4 times 4x minus 3 times x plus 2, and that is less than or equal to 0. We want to solve that on the real numbers. So the way we start this off is by finding the roots of this polynomial. So it's like we're solving the equation x minus 4 times 4x minus 3 and then times x plus 2 equals 0. So forget about the inequality for a second. Just imagine it is equality. And what are the solutions to this equation? Well, each factor corresponds to a solution according to the zero product property. First of all, there's x minus 4 equals 0, and that gives us a solution x equals 4. There's also 4x minus 3 equals 0, and that gives us a solution, add 3 to both sides and divide by 4, x equals 3/4. And lastly, x plus 2 equals 0. Just subtract 2 from both sides to get x equals -2. Okay, so now that we've got our roots, let's plot these roots on a number line. So we'll have, how about the smallest one? -2 can go over here, -2, and then what's next? 3/4. We'll put that roughly over here, 3/4, and then the last one will be x is 4. Now notice that these roots divide our number line into 4 intervals. There's the interval from -infinity to -2. Let's write that down here. -infinity, -2. There's also the interval from -2 to 3/4. Let's write that here. -2 to 3/4. Going on 3/4 to 4. And then 4 to infinity. Now, the reason that we're partitioning our number line into all these intervals is that our polynomial on the left-hand side, it's going to have the same sign throughout any given interval. So if our polynomial is less than or equal to 0 on somewhere in some interval, then it's going to be less than or equal to 0 on that whole interval. Now we've just got 4 intervals that we need to check. Is it less than or equal to 0 on each of these intervals? To organize all of this, we're going to use a sign table. So let's go ahead and write our intervals in the top column. There's -infinity to -2. And then we'll also write down our roots here, -2. And then the next interval, -2, 3/4. And then the next root, 3/4. And then the next interval from 3/4 to 4. And then the next root of 4, and finally the last interval from 4 to infinity. Now the goal of this sign table is to figure out what is the sign of this polynomial on each of these intervals. For any given interval, is the polynomial positive or negative on that interval? Why don't we start off by just looking at the roots here? We know that at the roots, the polynomial is just 0 on that interval. So we can skip through the whole test value and factors process for the roots. Don't worry about that just yet. But the idea is that at -2, for example, the polynomial is just 0. And at 3/4, for example, the polynomial is just 0. And at 4, for example, the polynomial is again just 0. But between the roots, the polynomial is not going to be 0. It's going to be either positive or negative. And the way we can find that out for each interval is by choosing a test value within that interval. So for example, for this interval -infinity to -2, we could choose a test value of, say, -3, because -3 is inside of that interval. We could also choose -4 or -5, -1,000,000, but we want numbers that are easy to work with, easy to plug into the factors of the function here. So -3 is kind of the easiest number that we can pick within that interval. So now let's get the sign of each one of these factors. We don't really care what number it evaluates to, we just care whether it's positive or negative. So first of all, when we plug in -3 for x in this factor x minus 4, we get -3 minus 4, that's -7, but all we really care about is that's a negative number. And let's do that the same thing for 4x minus 3. When we plug in negative 3 there, that's negative 12 minus 3, negative 15. Again, a negative number. And when we plug in negative 3 for x in this last factor, x plus 2, we get negative 3 plus 2, which is negative 1. Again, a negative number. So at this value of x equals negative 3, the polynomial is really just a negative number times a negative number times a negative number, and 3 negatives multiplied together, that makes a negative. So the polynomial is negative at x equals negative 3, and also it's negative everywhere on this interval. Now let's do the same thing for each of the remaining intervals. Let's choose some easy test values here. So negative 2 to 3/4. How about 0? 0 is always like the easiest test value by far if we have it inside the interval, and indeed it's in that interval. So let's plug it in here. 0 minus 4, negative 4, that's negative. 4 times 0 minus 3 is just 0 minus 3, so again, negative. Now 0 plus 2, ooh, that's positive. Okay, so our polynomial is just a negative times a positive, which makes a positive. Alright, looking at the next interval, 3/4 to 4, how about let's choose 1 there? So 1 minus 4, negative 3, that's negative. 4 times 1 minus 3, that's just 4 minus 3, and that is positive. And 1 plus 2 is 3, which is positive. Okay, so our polynomial at this interval, it's going to be negative times positive, so just a single negative sign, so negative. Lastly, our interval 4 to infinity, let's choose a test value. How about 5? So 5 minus 4, that's going to be positive. And then 4 times 5 minus 3, that's 20 minus 3, 17, positive. And then 5 plus 2 is 7, which is positive. Positive times positive is just a positive. Okay, so now let's look back to our problem. We wanted to find where the polynomial is less than or equal to 0. So where it's 0 or negative. And now let's look back to our last row of our sign table. Where is the polynomial 0 or negative? It's negative here, it's 0 here, so we should include these. It's positive there, so don't include it. 0 negative here, and also 0 here, but then positive here. So include this, but then that's positive, so don't include that. Okay, so let's take a look at what intervals those correspond to. So that corresponds to the interval negative infinity to negative 2, and also the point negative 2. So we should be including this in our solution, but not this interval because it's positive there. The function is positive there. And then we should be including this interval also with its 2 endpoints, which are roots, but not this interval because the function always evaluates to positive there. Okay, so let's go ahead and write that down. So this interval, along with the endpoint negative 2, that can be written as negative infinity to 2 with a bracket to say that we're including that 2. And then this interval, including 3/4 and 4, so that can be written with 2 brackets, 3/4, comma 4, to show that we're including both endpoints. And so we have just x is an element of either of 2 intervals. So element of negative infinity 2 union 3/4 4. And there we go. We've got it. Alright, here's another problem which is pretty similar to the previous one. We're solving a polynomial x to the 4th minus 4x to the 3rd minus 12x squared is greater than 0 on the real numbers. The only difference here is that our polynomial is not factored yet, and also this is a strict inequality. It's greater than, not equal to. Okay, so why don't we start off by factoring our polynomial so that we can actually find the roots. So we can factor out an x squared from everything. So x squared times x squared minus 4x minus 12 is greater than 0. And let's go ahead and factor that quadratic also. So x squared times x minus 6 times x plus 2 is greater than 0. Okay, now we're ready to find the roots here. So using our zero product property, either x squared equals 0, which just means that x equals 0, or x minus 6 equals 0, which means that x equals 6, or x plus 2 equals 0, which means that x equals negative 2. Alright, so now we've got our roots, and let's put them on our number line. Negative 2 is the leftmost. We'll put that right here, negative 2, and then 0. We'll put that right around here, 0, and then 6 will be way over here, 6. We've also got our intervals from negative infinity to negative 2, and then from negative 2 to 0, and then from 0 to 6, and then from 6 to infinity. Now let's write all this in our sign table. So intervals will be negative infinity to negative 2. Then we'll put the root of negative 2 in the next column, and then interval negative 2 to 0, then root of 0, and then interval 0 to 6, and then root of 6, and then interval of 6 to infinity. Before we get started with test values, let's also go ahead and complete our sign table now that we know the factors. So first factor is x squared. Second factor is x minus 6. And third factor is x plus 2. And the full polynomial in factored form, that's just x squared times x minus 6 times x plus 2. So again, we're trying to figure out what is the sign of this polynomial on each of these intervals. Why don't we start with the roots? We already know that the roots cause the polynomial to go to 0. So put 0 for each of the roots. And now we'll deal with the actual intervals. We've got to choose some test values here. So for the first interval, negative infinity to negative 2, how about a test value of negative 3? And we'll plug that into each of the factors. Negative 3 squared, well, a negative number squared is always a positive. Negative 3 minus 6, negative minus positive is always a negative. And then negative 3 plus 2, the negative 3 is greater magnitude, so the negative sign stays. And then when we multiply all that together, positive times negative, the two negatives cancel out, and we've just got a positive for the function. Okay, next interval, negative 2 to 0. How about a test value of negative 1 there? Negative 1 squared, negative squared is still just a positive. And then negative 1 minus 6, that's a negative. Negative 1 plus 2, the 2 is higher magnitude, so positive here. And then we've got a positive times a negative times a positive, and that comes out to negative. Next interval, 0, 6. So test value, how about positive 1? So positive 1 squared, that's still positive. Then positive 1 minus 6, the minus 6 has a bigger magnitude, so negative. And then positive 1 plus 2, positive plus positive is always a positive. Okay, so we've just got positive times positive, and again a negative. And last interval, 6 to infinity, how about a test value of 7? 7 squared is a positive. And 7 minus 6, just 1, that's a positive. And then 7 plus 2, positive plus positive, just a positive. And then positive times positive is a positive. Okay, so let's look back to our original inequality. Wanted to find where that polynomial is greater than 0. So just where it's positive, not where it's 0, not where it's negative. So here's a positive, but we don't care about the 0 and negative. Still don't care about the 0 and negative here, still don't care about the 0 here, but we do care about the positive here. So looking at those positives, positive interval was that one, and then we don't care about everything in between, and then positive interval, that one. So our final solution then is just the union of these two intervals where the function is positive. So x is an element of negative infinity to negative 2, union 6 to infinity. And there we go, we're done. In these exercises, the right-hand side here was always 0. In the future, though, we'll also learn how to deal with cases where the right-hand side is a polynomial itself.